So integration by substitution, aka U-substitution, or the reverse of the chain rule, right? So we've kind of intuited some of these, done them by guess and check if you like, and if that works for you, that's fine, right? So if it's on a test, you look at it and you say, oh yeah, I can see what the integral will be, then just make sure that it is in fact, right? But if not, then we need a method to fall back on, right? It's like factoring a quadratic. If I can't figure it out, well, I've always got the quadratic formula I can use, and then at some point during the quadratic formula, you realize, oh, wait, it would have factored, and those are the factors, but so what, right? In other words, we've got the thing. So if we look at something, cube 7 dx. Okay, so we might be able to figure this one out without doing this U substitution stuff, but let's see how we will do it with this U substitution stuff. Okay, and again, if you can figure it out easily without, or reasonably easily, you try guess and check, right? So like, yeah, I'll give it 30 seconds, and if I can't figure it out, then I know I can do U substitution. So here's what we do. We just do something a little bit simpler, right? We're going to let U, now we know that the derivative of the inner function here, right, the 5x cubed plus 7 is going to be the 15x squared, okay? So what we do is we let U equal 5x cubed, so let U equal basically the inner function, the 5x cubed plus 7. So du by dx, if we take the derivative of this, we just get 15x squared. And if we rewrite it as a differential, we get du is equal to 15x squared dx. So we see that, and I'm going to do this in a little more detail than we'll do subsequent ones, right? Just to kind of show you, hey, this is how it works. So let's rewrite this guy as cube root 5x cubed plus 7 times 15x squared dx. And we say, hey, 15x squared dx, that looks familiar because it's here, but it's also here. Which means that I could just write this as du. And u, well, that's this, so I could just put a u. Go ahead, open it. Okay. It's like ripping off a Band-Aid, right? It doesn't work. It's too painful when it's slow. So the 15x squared dx, that can be du. And I can just replace this with a u, or substitute, right? So we do that. So we've got the integral of the cube root of u du. So now everything's just in terms of u. All right, so that's easy to do, right? I mean, the integral of the cube root, all right, so what's that? Let's just kick this over here. So it's the integral of u to the 1/3 du. So what do? We increase that by 1, so it becomes 4/3. And then we divide by 4/3, which is going to become 3/4. So what's this integral? It's going to be 3/4 u to the 4/3. And what goes on here? Plus c. And we say, well, but look, the original question did not have a u. The original question had an x. So we'll just go back and we will replace the u with what it is, which is 5x cubed plus 7. So we get 3/4 5x cubed plus 7 to the 4/3 plus c. Okay, and we can check that because you can do the derivative of that. So 4/3 times 3/4 is going to be 1. The 5x cubed plus 7 will now be the power of 1/3, or the cube root, and the inner function gives me the 15x squared. So there we are, right? And maybe we could have figured out part of that pretty easily, right? I mean, we know the inner function gave us the 15x squared. Just getting that whole 3/4, in front, 4/3. You would have probably figured that out or intuited that. So that's U substitution. But we should do a few more. Now, how does it work, right? So it's if you're given something of the form. So U substitution, when let's say this, when given an expression of the form, like an integral of f of g of x, right? This kind of chain rule stuff, right? Where you got some inner function, g prime of x, right? Okay, now it just is a chain rule thing, expansion, right? Dx. Then we can write that as integral of f of u du, where u is equal to g of x. Right? So we have some inner function. We can see its derivative on the outside there, right? So the g prime of x. So we know this is a chain rule situation. If we let u equal g of x, then we can rewrite it as a function of u du. Now, sometimes we have to make adjustments for it, right? It doesn't look exactly like we want it to. So the first one looked exactly like we wanted it to. So that's a statement of U-substitution. All right, so there's our expression. What's our inner function going to be? 2x minus ln x. Okay. It's kind of good because what's the derivative of 2x minus ln x? 2 minus, good, right? Because we're getting the 2 minus 1 over x. Okay, so we start, and again, having seen that, you might be able to do this without doing U-substitution, but here's how you do it with U-substitution, right? So it just gives you something to fall back on if you're looking at it going, yeah, I'm just not seeing it. So you let u equal the inner function, which is 2x minus ln x. We then take the derivative of that, and we'll just write it in differential form. So really what we'll do is kind of the derivative of both sides. So du is equal to 2 minus 1 over x dx. Okay, so then we look here and we say, hey, so I've got that. It's just kind of split up, right? But if I write a du, I've taken care of those two terms. And, well, I know what this is. This is just going to be replaced with u. So we can now write this as the integral of sine u du. Okay, so to make sure things match up, the u is the 2x, so I've got the sine of 2x minus ln x, and the du takes care of the 2 minus 1x and the dx. Okay, so everything is present and accounted for. We do the integral, so what's the derivative of that, or the integral?
Negative cos u.
Negative cos u plus some arbitrary constant, right? Doesn't matter what the constant. And then we say, well, wait a second, never was a u. It's not u. It's 2x minus ln x. And don't forget the plus. Okay? And again, right, you might have figured that one out. You just said sines, oh, that's the, the outer part, that's the derivative of the inner part there, and what's the derivative of the integral of sine is negative cos, right? So if you can do it that way, you do it that way.
Yeah, it's the actual answer. It's a borderline L curl. It's like more you're done.
Okay, so we have the integral of 30x plus 5 and 3x squared plus x, e to the 3x squared plus x dx. So what's our inner function? 3x squared plus x. Now, there's a problem there, right? Because the derivative of that is 6x plus 1. Oh, okay, but we got 30x plus, that's okay. We can turn a 6x plus 1 into a 30x plus 5, right? All right, so we just start off by saying, okay, u is 3x squared plus x, which leads to du is 6x plus 1 dx. Now, I got a problem, right? Because I can't just, you know, I can't just put a du in there for the 30x plus 5. So we say, well, if I go 5 du, then I will get 30x plus 5 dx. So I can replace 30x plus 5 dx with a 5 du. Right? Make sense? Okay, so we had to make an adjustment there, right? And we've done that before. It's when you say, you know, when you've just looked at it and you said, oh, well, if I've got a 2 there, then I got to put a half in front to get rid of the 2.
Can you not just like put du into the equation and just write 5 times du in the equation without showing 5 du is equal to that?
Yeah, I mean, ultimately what we care about is that you do this. So you now say, okay, so it's going to be 5 e to the u du. Okay, so just get the 5 somehow. Right. So yeah, you can write the du as 6x plus 1 dx and realize, okay, I'm going to have to put a 5 du in there. I've just made it explicit. Some people are just like, hey, I want to see the stuff I'm replacing, the 30x plus 5 dx. I want to see that, right? And sometimes it's a little more complicated. It's just handy to say, hey, let's take this multiplied by 5.
Okay.
Now, we know from our properties, right, that if I have a constant, just move the constant out front, right? So e to the u du. And what's the integral of e to the u? E to the u. So this will be 5 eu plus c. But that's not the end. What do? We go back and we say, what was u? Yeah. 3x squared plus x. Okay. And a lot of you wouldn't be able to figure, you know, you would have figured that out. Well, this is 6x plus 1, that's so I need to multiply it by 5, and then we'll just leave it. Okay. Which, if you can do it that way, it's fine, right? So it's just formalizing a method is just an alternate. But it can come in handy in certain ways. Okay, 3x over the square root of 1 minus 3x squared dx. So you might want to rewrite this. Like this. Get it all in one line, right? We know the inner function is 1 minus 3x squared. We know the derivative of that's going to be negative 6x. So we're going to have to get a negative 2 somehow, right, to get that 3x to be a negative 6x. But let's just kind of formalize it, right? So we'll say, okay, u is 1 minus 3x squared, which leads us to du is negative 6x dx. And say, but I want a positive 3x dx. So what am I going to have to do? Negative. What do you multiply negative 6 by to get positive 3? Negative 1/2. So I say negative 1/2 du is equal to 3x dx. Right? Now you don't need to show that line, right? You just have to know that I'm going to have to throw negative 1/2 in there. I like to show it because it tells me I got a 3x and a dx that I can see right up there. And instead of that, I can just write a negative 1/2 du. Right? So it's a direct replacement. I'm looking at this. I see it here. This could just be written as negative 1/2 du. This is just u to the negative 1/2. So we now go over here. We say, what do we got? Well, we got u to the negative 1/2 times negative 1/2 du All right, as a constant, let's just throw it up front. Okay. If that's too many steps, just imagine a line written above it, which is u to the negative a half times negative a half du, and then move the negative half up front. Okay, well, u to the negative a half, that's easy to do, right? All we got to do is add 1 to that. So I have the negative 1/2, right? That's from here. Add 1 to this, we're going to get u to the 1/2. What else do we need? Need a 2, right? Because this is going to come down as a half, but we've got a 1, right? This would be a half u to the negative a half, so we've got to put a 2 there. And we need a plus c. Now the plus c, actually, it can be written in the brackets, out of the brackets, doesn't matter, right? It's some arbitrary constant. If I write it in the brackets, it's now negative 1/2 of what it was. But it doesn't matter because it was just an arbitrary constant. So sometimes some people might write like, oh, that's going to be like C1 because now you've multiplied it, so it's a different arbitrary constant. But to me, it's just a constant. Okay. Yeah, so this becomes negative a half times 2 is negative u to the 1/2 plus c.
Yeah, okay.
Negative a half times 2, right? This had to go up by
But you
1.
don't multiply negative 1/2 by c. You just
It's another constant.
It's as if I never said it, right?
yeah.
It said, is there work, after I explained, is there a work, there's no worksheet today, right? Is there a worksheet today? You're operating on a lag. You can just rewind. Rewind. Okay, here, for you. Okay. For everybody else? Right. It's an arbitrary constant, so it doesn't matter. Right? And you'll see this in a little while, and then we'll get the question shortly after. You'll see this in a little while where we have a constant inside of here, like plus 4. And you got plus c. Just roll them together. Right? And then you can ask about it right after I do it. It's okay. It's the internet. Nobody knows who you are. Okay, but it's really... I don't have to go into... You know how tough it is to edit sound? 1 minus 3x squared. So u is 1 minus 3x squared, so it's negative 1 minus 3x squared to the half plus c. Right? And some people like to write c1 and then it changes, becomes c2. Right? So that's fine. So if you're disturbed by that, how can it be the same c? Then just write a little c1 there and then change it to c2 and you've multiplied it through. It's fine. Right? It's just a different arbitrary constant.
Oh.
Do you see? Okay, questions? Kind of straightforward-ish stuff. When I give you, so there is a worksheet for this. The worksheet for tomorrow is just basically a question sheet. Looks a little bit like this. Actually, it looks more like this. And some of the answers were wrong on that one.
Is that it?
Yeah, that's for tomorrow. This is worked out solutions.
Woo! Fun.
Oh, 4 pages. That's 5?
5 pages. Yeah.
Front and
So we
back?
make it-
No.
Oh,
I just did them single-sided. But what I'll do is I'll scan them in and I'll stick them up and I'll put them on the board tomorrow or whatever so you have access.
Wow.
Okay.
Slick.
But continuing, because we got a few more to do. Oops, no, it's all right. There's 3 over x ln x dx. Okay, so you think about it and you say, well, my inner function is ln x, right? So u is equal to ln x. Then what's du? Yeah, let's go, 1 over x dx. You can write as, I like to write as 1 over x dx. But what have we got in the original? We really have kind of a 3 dx, right? Like 3 over x dx, right? So if I say 3 du, that'll be equal to 3 over x dx, right? So 3 over x.
Oh, yeah.
dx. Okay. So everything circled in green can be replaced by du, and we're left with 1 over ln x, right? So it's 1 over ln x times, let's just split it out. I'm going to split it out this way. Just makes it a little more clear what's what. Okay, now we can say, oh hey, okay, so that's the stuff that you circled in green. So let's pull the 3 out front. We get 1 over ln u du. Oh, sorry, it's just 1 over u, right? Because u is equal to ln x, so this becomes 1 over u du. Okay, well that's doable. What's the integral of 1 over u? Ln u. So 3. Okay, ln absolute value of u, right? Ln's got to be positive. Plus c. Don't forget the plus c. Okay, but what was u? So it's the ln of the ln of x.
Do you need to put the absolute value sign if ln can't be a negative value?
So can x not be, well, yeah, you're right, because in the original there's a ln x, so, okay. Ln x plus c. So the ln of the ln. Now that might be one that you wouldn't have figured out intuitively, right? So that, you know, there is a place sometimes for this. You know.
That's fine. Sweet time.
I didn't hear what you said.
Okay. 5x squared plus 4. So who's you? I am me. You are you. 5x squared plus 4, right? Okay, so you. So du is 10x dx. Okay, but we've got what? We got a 3 there, right? So what are we going to multiply? What's our constant going to be? You okay with 10?
5x squared. Yeah. How dare you?
10x anymore?
Am I right?
No,
Yeah.
you are not.
Okay, but we don't have a 10 dx in there. We don't have a 10x dx. What do we have? Okay, so how are we going to turn a 10 into a 3?
Hold on, I was just 3 times 3.
Multiply by 3/10.
This is my shit. You're trying to say I'm wrong.
So 30 over 10.
So 3/10 du will be equal to multiplying by 3/10 3x dx, right? So we now get to replace the 3x dx with 3/10. Now, 3/10 being a constant, we can just put it out front. Okay. So next line we're going to write is 3/10 integral. Okay, so we've taken care of the 3x dx. We now have this, which will be 1 over u du. Well, I was getting last year's notes. It took like 6 lines to get there.
Hey, let's.
Does it make sense, right?
Yeah.
Okay, good. All right, well, it's pretty easy. What is it?
3 times ln u plus c.
We'll go with the ln of the absolute value of u in this case, right? Because that can be. Although wait, 5x squared plus 4 is always going to be positive, isn't it? All right.
Sure.
Okay.
That was totally intentional.
It must have been.
Well, it doesn't really matter.
Well, in this case, u is going to be positive, right? Because it's 5x squared plus 4. So it's never 0, it's always positive.
It never hurts to put it in.
Well, and again, yeah, it doesn't hurt to put it in, right? So if you want to, you put it in.
It does if you have our brackets.
Okay, so
Well, then you should be in this class. Right. I'm not saying that.
and then
I kind of think it's
u is 5x squared plus 4, so it's 3/10 ln 5x squared plus 4 plus c. Okay, so at this point, you look at it and say, I could have done that without doing this stuff, which, you know, it's fine, as long as it doesn't say, by using U-substitution to show the following, you know, if it's just a multiple choice, you pick it up.
You gotta do. And we're done. You gotta do.
Oh, we're nowhere near done.
Nowhere near done. God, 5 more, right?
It's 2 pages in, and I got 4 pages left.
Oh,
Hey, there's a lot to see here.
Is it all?
Now, actually, so up till now, it's been pretty indefinite, right? It's indefinite integrals. We're now going to do definite integrals, and there's a neat thing that happens when you do U-substitution with the definite integral. So,
Are we all gonna say whoa?
well, not yet.
This puts us at 20 maybe.
You heard that on.
Whoa.
1 minus 4x cubed.
Whoa!
Not yet.
Oh.
Okay, so here's the definite integral from -2 to 0 of 2x squared times the square root of 1 minus 4x cubed dx. And you might say, well, you know, I could do that just using, you know, sussing it out, but let's see what happens when we use U-substitution. So we're going to start with u is equal to 1 minus 4x cubed. Du will be -12x squared dx. Okay, we don't want a -12, we want a +2, so what are we going to multiply by to get +2? -1/6. It's okay, just think about multiplying, you know, if you actually carry it out, if you did the 6, you're going to end up with a 72, so you should say, that's not quite right.
That's not right.
That's not right, I can't do that. Now, here's where something a little different comes in, right? Our bounds of integration were for x. Now, if we're going to write this in terms of u, then we need our bounds of integration to be for u. So we say, oh, well, when x is equal to -2, well, we know what u is. We've got an expression here, right? U is equal to 1 minus 4 times -2 cubed, which is what? That's 8, -8, 32, 33, just call it 33. And our upper bound is 0, which is going to be a lot easier to work out. So 0 is just u is going to be equal to 1. I don't know. It says no internet on computer, and then Ari got it. So it's like, why are you? Like, am I in the house? Am I going to fix the internet on the computer from here? When you know, there's somebody at home who actually knows this stuff.
Maybe she just thought you wanted to know.
Yeah. Like, oh, so I should have replied, ask me if I could know. Okay, so now what do we have? Well, we have the definite integral with a lower bound of 1 to an upper bound of 33. The 2x squared dx has been replaced with -1/6 du. The -1/6
Wait a minute and a half.
can simply come up front. We now have the square root of u, so just u to the 1/2 du.
Oh, God.
Okay, so makes sense so far? Okay, so -1/6, just constant, just comes out in front, right? And there's the -1/6 there, which we wrote out explicitly, so we get the 2 and not a 72 or something. Okay, and the negative, so that the negative 12 would become a positive 2. Okay, but now we have to adjust the bounds of integration, right? Because u goes from 1 to 33, whereas x goes from negative 2 to 0. All right. Now, we don't need any plus c's here because we're actually evaluating. Okay, so first, what is the, what's the integral?
Who knows?
I don't know. Somebody knows.
It's
Yeah, 2/3 u to the 3
2/3 u
halves.
to the 3 halves.
2/3 u to the 3 halves?
Plus c, but it doesn't matter.
Don't need the c.
Don't need the c. Don't need the c.
Definitely don't need the c.
Don't need the cancers.
Okay, but we do need to evaluate that from 1 to 33, right? Lower bound of 1 to an upper bound of 33. All right, so we have a constant inside that can just come outside, right? So we can do the negative 1/6 times 2/3, which will be
2/18.
okay, or 1/9, but it'll be negative. Oops, don't need the 2/3 now. All right, so we've got negative 1/9 times, then we're just going to evaluate this. Okay, so upper, so we got 33 to 3 halves minus 1 to the 3 halves. Right, wait a sec. I think I've done my numbers backwards. Oh, sorry, the negative 2 was a 33. I reversed all these. The negative 2 was the 33.
Maybe a little too much.
So that's the 33. So there. Point to note. Watch what's what. When x is negative 2, u is 33. So we go 33 on the lower bound there.
Whoa! Ah!
Well, not yet. Actually, it's too late.
I didn't say whoa at first.
I mean, I said whoa.
I was surprised.
Yeah.
I mean, if you're gonna reprimand me every time,
Let that be a lesson for. So watch what your bounds of integration, because when they change, it's not always just, hey, the lower number goes on the bottom and the upper number, right? When x is negative 2, u is 33, and when x is 0. So where I see the negative 2, I need to be putting the 33, and where I see the 0, I need to be putting the 1. And I accidentally reversed those. So this will be 33 to the, no, it'll be the upper. It'll be 1 to the 3 halves minus 33 to the 3 halves. Okay, so that's negative 1/9. Then we're just going to play around inside the brackets here. It's going to be 1 minus 33 to the 3 halves. Let's just kick up here and we can just kind of play with this a bit. What's 33 to the 3 halves, you ask? So it's 1 minus 33 root 3. Root 33. Now we've got that negative 1/9, so we'll just distribute the negative in. Leave the 1/9. Reverse the signs here. And end up with that as an answer, right?
Wait, what do we just say? Whoa.
Oh, yeah, it's too late. I don't know.
Whoa!
That'll work.
You can like take that audio and then put it more.
Yeah.
Like the
I try to keep edits to a minimum. All right, so moral of the story. Number 1, you change your limits of integration. Number 2, when you do it properly. Always have an eraser handy.
Or have 3.
Yeah. Then have a backup eraser.
And another one. I mean, or you can go along with having a side.
Okay, so definite integral, negative, sorry, not negative, the square root of pi over 2 to the square root of 3 pi over 2 of x cos x, oh, sorry, copy that down. It's, whoa.
Whoa.
X cos x squared dx. So not cos squared x, but the cosine of x squared dx.
Oh my god.
All right, so the inner function is the x squared, and du is 2x dx, and we just have an x dx. So if you like, you could say it's going to be 1/2 du is x dx. So the x dx, by now we should be getting used to this. The x dx is going to be replaced by du. But when we replace this stuff, right, we're going to have a function in terms of u, not in terms of x. So we have to work our bounds of integration. So when x is equal to the square root of pi over 2, u is just equal to pi over 2, right? Because u is x squared, so that worked out nicely. And when x is equal to the square root of 3 pi over 2, u is x squared, so it'll just be positive 3 pi over 2. All right, so we have new bounds of integration, which are pi over 2. Let's match them up properly. So the root pi over 2 is pi over 2. 3 pi over 2. The x dx is my du, and we've got cosine of u. So it's cos of u du. All right, what's the integral for cos u? Sine u. Yeah. Okay. Oh, wait, the half, right? There. Sorry. Throw that half in front. Okay, so we've got 1/2 sine u evaluated with a lower bound of pi over 2 and an upper bound of 3 pi over 2. So that's 1/2 sine 3 pi over 2 minus sine pi over 2. What's sine of 3 pi over 2? -1. What's sine of pi over 2? So we got a half. We got -1 minus 1, which is a half times -2, which is
Okay.
-1.
Ready?
Okay.
Whoa! I didn't know what you were gonna do.
Well, then why are you ready for what? It's on 3.
I was
What?
gonna go with it.
I was waiting for that game to go into the 4th overtime period.
Oh my, that would've been so cool. It's already the longest game.
It was Blackhawks, but the Ducks had gone 5 overtimes once. They were getting a little tired, it seemed.
Like you just played at like 3 o'clock in the morning.
That was on the West Coast. It
We're not
wasn't
gonna
even
break
late.
at this point. I think you actually
Okay.
do have to just keep playing until there's a goal. At some point, one of the
What if you
boys
play
just
to the
flips
next
it
play
out
on
the
the
game.
Somebody's gonna get really tired.
An hour later.
Okay, one more definite integral and then some other stuff.
It's kind of bad actually, like play in my game.
Yeah.
Sick.
They end up signing free agents just to play in the game.
It's like getting people from the crowd and be like, shoot.
Okay, so we've got definite integral from 0 to 1/2 of e to the x plus 2 cos pi x dx. Okay, I suppose really probably this should all be in brackets here, right? Well, we could split that up, right? Because it's the integral of a sum, and from the 2 properties we learned yesterday, one of which we've now used extensively, which is moving the constant out front, we can write that as the sum of 2 integrals. So 0 to 1/2 e to the x dx plus the integral 0 to 1/2 of 2 cos pi x.
Could you pull out the 2 there, or would it make sense to keep it in until you've done the derivative?
You could pull out the 2 there if you wanted, yeah. Yeah, it doesn't matter. We'll pull it out in a minute. So, e to the x dx we could do, right? No fancy stuff required there. Right? Like this integral, doable, normal, integration, it's just e to the x. Okay, so we don't have to do anything special here, right? So keep that in reserve. We know that, yeah, we can do that. This line, we could probably do, but let's do the u substitution bit, right? So in this case, we're going to say, well, okay, I got this like pi x sitting here, right? So we're going to let u equal pi x. Then du is equal to pi dx. Okay. What do we want here?
1 over pi du equals dx.
Well, no, we need a 2 dx, right? So I got to get this to be 2 dx.
Do 2 over pi.
Yeah, so multiply by 2 over pi, right? So 2 over pi du, multiply this by 2 over pi, we're just going to get 2 dx, right? So we got to look at what are we trying to turn, like what are we trying to cover off here, right? Which is we're trying to get that 2 dx. I need to get a 2 dx. What am I going to replace with? Well, 2 over pi. And that's the constant that we're actually going to go and stick out front, right, is the 2 over pi. So instead of doing the 2 now, it's better to leave it in there so that you're saying, hey, I want to get rid of this 2 dx, right? Or I want to replace this 2 dx. What? With what? With 2 over pi du. Okay, and then what's the cos? Just going to be the cos of u. Okay, so we've got 0 to a half e to the x dx plus, okay, wait, when we replace this with a u, these are for x's, right? X goes 0 to a half. So we still got to go over here and say when x equals 0, what's u equal to? Just 0. U equals 0. When x equals 1/2, u is equal to 1/2 pi, pi over 2. Okay, so now make sure we're getting the right stuff. Yeah, okay, so this is the 0. The 1/2 is a pi over 2. We're going to take the 2 pi, 2 over pi, that's just a constant. We'll throw that out front. So 2 over pi. 0 to pi over 2. Cos pi x is now u. And the 2 over pi du is the 2 dx. Okay, so just kind of make sure, yeah, is everything accounted for? Yeah, the 2 dx has been taken care of with the 2 over pi and the du. The pi x is now the u, and the bounds of integration, instead of x is 0, it's now u is 0, and when x is a half, u is pi over 2. Okay, so now we're ready to integrate. This will just be e to the x evaluated from 0 to a half plus 2 over pi and the integral of cos u, sine u. And its bounds are 0 to pi over 2. Okay, so working everything out, I guess we toss some equal signs in here. That. So this will be e to the half minus e to the 0 plus 2 over pi times the sine of pi over 2. As a matter of fact, let's just expand the whole thing out. So let's go 2 over pi times the sine of pi over 2 plus 2 over pi, or sorry, minus 2 over pi times the sine of 0. Okay, so we've expanded that out. We're going to e to the half minus e to the 0. I've taken the 2 over pi times the sine of pi over 2 minus, and then the 2 over pi again is going to multiply, right? So we've done the expansion and distribution in one step. That's just 0. That's a 1. That's a 1. So we got e to the half minus 1 plus 2 over pi minus 0. I guess you don't need to write that. So that's it. E to the half minus 1 plus 2 over pi.
Plus c.
Nope.
No plus c.
It's a definitely no plus c.
It's a chill
Yeah.
absorption.
We could go minus 0.
Or plus 0. Up is 0.
Yeah, but it was minus 0.
But we could have done infinity times 0. It's going to be
Let's just do that.
All right, so if that wasn't enough, then we have substitution part 2. This is only 4 pages.
3?
4.
Wait, how many have you gone through right
2. How many we've gone through? 1, 2, 3, 4. We've gone through 10.
now? Really? How many more are there to go through?
4. 10, 4.
14?
No. Yeah, there's 14 in total.
Oh, oh.
Well, that's 14 boards of stuff, right? They had, this is what the worksheet kind of looked like, and I just thought there's not much room on that to write this stuff down. So. Yeah, it's, okay. Substitute, if we have a monomial denominator, let's say we're doing the integral of x plus 1 over x dx. Then we can split it up, right? It's like writing 3 plus 7 over 4. Well, that's 3 over 4 plus 7 over 4, right? I mean, normally we'd say it's 11 quarters, but you can split it out. So this can be split. So can be split. So it's the integral of x over x plus dx plus the integral of 1 over x dx. All right, so you can split that out. That's pretty easy to work out, right? It's just the integral of 1. So that's a 1 plus 1 over x dx. So I've just recombined them, right? Sum of integrals, the integral of the sum. And it's just a way of rewriting x plus 1 over x, right? As 1 plus 1 over x. And it's pretty easy to do the integral of that, right? The integral of 1 is x, and the integral of that is the ln of the absolute value of x. And we'll need a constant on the end. Okay, so nothing fancy there, right? If it's a monomial denominator, you can just split it up as a sum, individual parts, works out pretty easy. Binomial denominator, this could be a problem. And did I leave myself room to do this? All right, let's try this here, binomial. So what if we have x over x plus 1 dx? So here we have a binomial denominator. It's just flipped over, right? Well, in this one, yeah, we can't split it up. So what we're going to do is we're going to let u equal x plus 1. Now, you look at it and you say, okay, so on the bottom you're going to have a u. And up top, I don't know what you're going to have, right? Because you can't have an x and a u. We can't rewrite this and have the integral of x over u, d whatever, d what? So, well, we could say, hey, if u is equal to x plus 1, and I guess we should do our du here, right? So du is just equal to dx. But what's x equal to? X is equal to u minus 1. So now I can write this, and it's the integral of u minus 1 over u du. And what's that got? Oh, it's got a monomial denominator. Okay, we can do that. Let's do this an alternate way. There's an alternate way of working the monomial denominator. So that was one way, split it up. Here's another way. Just write it as u minus 1 times u to the negative 1 du. And you can go through and multiply by u to the negative 1, which gives you a 1. U times u to the negative 1 is u to the 0, which is 1, minus 1 over u du. Basically what we did there, right? We did that by splitting fractions. We did this by multiplying by the denominators of power, negative. We got the same results, pretty much. Okay, and what's this? Well, that's u minus ln U plus C. There's equal signs all the way along there. Now what's U? U is x minus 1, right?
Oh, it's maybe you don't want anymore. I get it.
He's throwing it up with your.
Ow.
She's giving it to you.
Okay, now, you ready? Yeah. Is U x plus 1? Yep, U is x plus 1. Thank you. And an easy change without having to erase anything. Now, what are we going to do with that plus 1? We can roll it into the constants. Okay? Now what do you say to that?
Why isn't it constant plus 1?
No, that's Harold's one. Okay, so if there's a constant in our expression, right, then we can just roll that into the 1. And if you like, you can write C1, C1, and then C2. Just to indicate that it's a different constant. I initially chose an arbitrary constant of 6, and now you've made it a 7.
How dare you? Is this how you communicate your rate with us, Harold?
Okay.
Spilling water.
Yes.
I suppose it is.
Oh, if I got, don't use the Kleenex. It's too.
I'm gonna be a better.
Look it up, man.
I'm gonna sit here.
He's gonna dirty the table.
Okay, what if we have a monomial radicand?
Doesn't matter. Filling the water is water. It's like radicand.
Monomial radicand, a single term underneath the radical sign. Right? Well, we just multiply that through, right? That's just an x to the 1/2. So, okay, so what's x to the half times x, right? It's going to be x to the half. What's x to the half minus 1? It's going to be x, or sorry, that's x to the 3/2, right? So x to the half times x to the 1 is x to the 3/2 minus x to the 1/2 dx. They're just individual things. We can work them out, right? We just got to add 1, so 3/2 becomes 5/2, then multiply by the reciprocal, so it'll be 2/5. So 2/5 x to the 5/2 minus, add 1 will be 3/2, multiplied by 2/3, yeah? So minus 2/3 x to the 3/2 plus some arbitrary constant. Okay, it's a monomial radicand, right? That's how you'll handle that. Versus the binomial radicand.
Oh my god.
That's like double as hard.
Oh, it's like, yeah, well, wait till you see the final answer. So we're going to start with u is equal to x minus 1.
Is the final answer going to fit?
The final answer is 2/15 x minus 1 to the 3/2 times 3x plus 2 plus c. So it's not something you would have intuited or done a guess and check on.
No.
Okay, so there are, there's a lot of times we could just do guess and check or intuit it, right? I mean, you did that on the test for a number of them. There was chain rule involved, but it wasn't difficult. But this is not one of those ones. So u is equal to x minus 1. So that's going to be the u, but now we got to replace the x, right? So x is equal to u plus 1, and du is just equal to dx. So the dx, that's just going to be replaced by the du. The x is going to be replaced by u plus 1. So it's the integral. So the x is replaced by u plus 1. The root x is replaced by root u. And the dx is replaced by du. Well, okay, that looks an awful lot like what we did, right? Except there's a plus sign instead of a minus sign. But the idea is now we've changed a binomial radicand. No, binomial? Yeah, binomial, two terms. We've changed a binomial radicand into a monomial radicand. Okay, so we can do this. This part's relatively easy. It's the simplification afterwards that takes a while. All right, so what do? Well, you just multiply through, right? So this will be u to the 3/2 plus u to the 1/2 du. All right, pretty easy, right? Just add. So we got 5/2 and 2/5, right? So it's going to be 2/5 u to the 5/2 plus add. That's going to be 3/2. So 2/3 u to the 3/2 plus, let's call it C1. And if we change it to C2. We'll move it to C2. Okay, so you don't really want to substitute the x in right now for the u. We want to simplify this expression. And in a sense, we could have also simplified this expression a little bit, right? We could factor. So what's our common factor? Well, we got a 2, and we got to go with the lower power, right? So 2u to the 3/2 will be the common factor. So this becomes 2u to the 3/2. What are we left with? So this will be a u over 5, and this will be 1/3. Okay, so we're going to take the term inside the brackets and combine that together, right? So it's going to be over 15, right? And it's going to be a 3u plus 5 over 15, I think. Yeah, let me know. Throw some equal signs in here. So 2u to the 3/2, and this will be 3u plus 5 over 15. Okay, well, the 15 is a constant, right? So it can just come out as part of this, right? So it would be 2/15 u to the 3/2, 3u plus 5 plus c. Okay, now we can put the, what is it, x minus 1. So now instead of u, now we'll put in the x minus 1. So 2/15 x minus 1 to the 3/2, 3 times x minus 1 plus 5 plus c1. This can expand out. Let's extend the page. X minus 1 to the 3/2, which gives us 3x minus 3 plus 5, or 3x minus 2. Oh, wait, minus 3 plus 5 plus 2. Plus C1, and disappointingly it just stays as C1, right? There's no other constant. Yeah, there's no C2. Nah, no progression. Okay, so that's your answer, right? Which would be a little difficult to. Now, you can also, there may be a way to, there's alternate forms of this. Like they're identical, but it's just written in a different form. So this is the form where we're simplifying the u's, we're factoring stuff out. This is generally the form that you would see it in, right? And then we're putting the u back in and simplifying this expression. All right, we're on the last page. It's double-sided though, so.
Oh, so the other one's double-sided?
Oh yeah, they've all been double-sided. So
Oh.
there's only 7 pages in the book.
So only 2 more problems?
There's only 2 more problems.
You said there was 14 problems.
Yeah, 7 pages. Well, 14 boards. Yeah, just if you go to the room across the hall or kitty corner, they've got paper towels should be sitting.
I don't understand.
Grab more than you think you'll need, because you'll need more than you think you need. Okay, so what are we gonna do? We're gonna let the u equal the x plus 1. Okay, that'll give us a u squared on the bottom. Okay, which is fine. We can deal with that. So let u. And then we've got that 2x, right? So if u is x plus 1, we can't put like a 2u up top or anything, right? So that means that we need x is equal to u minus 1, and du is equal to dx. All right, the 2 is a constant. It could just come out front, right? So 2, right? Because we didn't need a 2 dx. Right? So it's not like we're replacing a 2 dx with the du. We've done that before. We're not doing that this time, so the 2 just comes out. X is u minus 1, and the bottom is u squared. Okay, and then the dx, that's a du. All right, you got a monomial denominator. We'll just bring it up top, write it as u to the negative 2, multiply it. We'll just have 2 terms, right? So we've got 2. Got a u minus 1 up top. We got a u negative 2 on the bottom. Or sorry, u squared on the bottom comes up as u to the negative 2. We multiply that in through this set. So this is 1 minus 2 is negative 1 minus u to the negative 2 du. And now it's time to integrate. So u to the negative 1.
Log of the absolute value of u.
Yeah, because u to the negative 1 is just 1 over u, right? So the integral is ln absolute value u. U to the negative 2. Now we got to up the power by 1, right? So negative 2 plus 1. Yeah, it's u to the negative 1, right? And that's going to be so plus u to the negative 1 or 1 over u. Okay? So you're right, it's u to the negative 1. So we take the power from negative 2 up to negative 1, but then we got to multiply by negative 1, which just change that to a plus. Plus C. Or let's do C1 here.
We get 2C.
Yeah. So that's equal to 2 ln absolute value u. Well, okay, wait, we could replace the u now, right? So what was u? X plus 1? So 2 ln absolute value x plus 1 plus 2 over x plus 1 plus C2, which is twice C1.
Oh my god.
Yeah, and you can just leave them as C's.
Magic color. More Harold.
Okay, last one.
This is what you get for asking a question. Harold floor. Harold floor, you stupid goon.
X root 3x minus 2 dx. All right, we get to end on a fun note here, right? So this is, well, we're going to start with u is equal to 3x minus 2. So that gives us root u, but we can't have x, right? The x has to be expressed in terms of u. So x is going to be u plus 2 over 3. And du will be 3 dx. Now, I don't have a 3 to go with the dx here, right? So the dx, I just want a 1 dx. So 1/3 du is equal to dx. All right. Instead of trying to put the constant out front first, let's just do a direct substitution, right? Integral. So x, that's replaced with u plus 2 over 3. Root 3x minus 2 is root u. The dx is 1/3 du. Okay, so what's our constant that's going to come out? 1/9.
Okay.
Right? So you've got what's in the denominator? We've got 3 and then 3, everything's being multiplied together. So 1/9. Okay, so what do we got? U plus 2, root u, du. Okay, that's good because I wasn't looking forward to integrating u plus 2 over 3, right? But that's just a constant, so we don't need to worry about that. So what are we going to do? Well, we're going to multiply through by u to the half, right? Okay, so this will be u to the 3 halves plus 2u to the half du. I lost an integral sign somewhere. Yeah. Okay, they're back in there now. Okay, now we can do the integral.
Yay.
Okay, so u to the 3 halves, again, just to add 1, it'll be 5 halves multiplied by the reciprocal, so 2/5 u to the 5 halves. Plus, okay, it's going to be u to the 3 halves times 2/3, so that's going to give us 4/3 u to the 3 halves. Oh, plus c, right? Plus c. So we'll do the c out here so it's not affected by the 1/9 in any way, shape, or form.
Yeah.
Right, like, so if you put it inside, oh, now it's 1/9 of what it was. And if you put it outside, then it's just is what it is. All right, so we need to take out a common factor. So what have we got? We got a 2 up top. Okay, so we're going to get 2/9, and we've got a u to the 3 halves. So this will be 2 over 9, u to the 3 halves. Okay, so the 2's gone, we got a 5, so we've got a u over 5. And that 2's gone, so we still have a 2, so 2/3 plus, and that's gone, it's just plus 2/3. Plus c. Okay, so we're going to take what's in the brackets, the u over 5 plus 2/3, and combine that.
Well, is that 2 different brackets?
Yeah, so I'm just going to clean that up. Extend page. Okay, so 2/9, u to the 3 halves. What's in here? We're going to get a 15 on the bottom. It's going to be a 3u plus 10. So the 15 can come out, right? So we got 9 times 15, which is 90 plus 45, which is 135. So bring to 15, we get 2 over 135, u to the 3 halves, 3u plus 10 plus c. So it's at this point that we can substitute in for the u, which is, well, okay, so we've got 2 over 135, u to the 3 halves, 3x minus 2 to the 3 halves, and 3u plus 10. 3. Oh. Maybe it ran out of ink when I wrote it. Was it 3u? So 3u, oh, plus 10. What am I doing? 3u, 3u plus 10 plus c. Okay, last little bit of cleaning up. So we get 9x minus 6 plus 10 plus 4 plus c. And that's the end of that. Thank you.
Whoa! Whoa!